Thermodynamics, science of the relationship between heat, work, temperature, and energy. In another word, thermodynamics deals with the transfer of energy from one place to another and from one place to another. The key concept is that heat is a form of energy corresponding to a definite amount of mechanical work. For this experiment, the objective is to apply the first and second law of thermodynamics in various processes, which is will investigate energy balance, determining heat exchange between hot and cold substance. This experiment will also illustrate energy loss from hot substance to cold substance and energy gain during heating. Law of thermodynamics states that the change in the system's internal energy is equal to the difference between heat added to the system from its surroundings and work done by the system on its surroundings. The first law is also known as the law of conservation of energy. The principle of energy balance is derived based on the first law. The second law of thermodynamics states that the heat does not flow spontaneously from a colder region to a hotter region, or equivalently, the heat at a given temperature cannot be converted entirely into work. Some examples of applications of the first law of thermodynamics in daily life. For example, the heat energy is converted into mechanical energy by the heat engine. Meanwhile, the use of refrigerating in our house is an example of application of the second law of thermodynamics. In the refrigeration cycle, work is applied to the cyclic system to allow the removal of heat from the cold environment to the hot environment. The scope of this experiment is to record the temperature changes at 1-minute intervals until thermal equilibrium is reached, and mass of the small and large beakers, both empty and half filled with water. Understand how the transfer of heat from the hot water in the small beaker to the cooler water in the large beaker progress over time. Law of thermodynamics states that the energy can neither be created nor destroyed. The energy can only change its forms from one to another. This is known as the principle of conservation of energy. Mass and energies such as heat energy and work energy can cross the boundaries of the system. Heat can be transferred in and or out of the system. In the closed system, the mass flow of the system will be constant. This means that in the closed system, only heat and work energy are able to transfer in or out of the system. Energy balance can be defined as the total amount of energy entering the system is equal to the total amount of energy leaving the system, plus the changes in storage of energies within the system. A system is composed of energies such as kinetic energy, potential energy, internal energy, and flow energy. When there is energy entering or leaving the system, it will contribute to the change in the energy balance of the system. For a closed system, there will be absence of flow energy as there is no changes in the boundaries of a closed system. The energy balance can be expressed as the equation down below, which E in of the closed system equal to E out of closed system plus total of E of the system. So we arrange it so that it can become E in closed system minus E out of the closed system is equal to the total E of the system, where so that the net of heat transferred by the system minus net work done by the system is equal to the changes in the internal energy of the system plus change in kinetic energy of the system plus change in potential energy of the system. Two statements to define the second law of thermodynamics. The Kelvin-Planck statement states that it is impossible for any device that operates on a cycle to receive heat from a single reservoir and produce a net amount of work. The Clausius statement states that it is impossible to construct a device that operates in a cycle and produce no effect other than the transfer of heat from a lower temperature body to a higher temperature body. So in this experiment, the hot water transfers the heat to cold water until thermal equilibrium is achieved. The heat transfer that occurs in this experiment does not operate as a cycle, and no network done supplied in the system. Assumed to be the experiment to be closed system, no input work means the work net is equal to 0, and so the equilibrium temperature is achieved. So the Q net will be equal to 0, hence the U net is equal to 0. So total E of the system is equal to 0. That means the total U of the system also equal to 0. So the total U is equal to total U of hot water plus total of cold water is equal to 0. So mass of the hot water times the specific heat capacity of the water times temperature 2 minus temperature 1 of the hot water plus the mass of the cold water times specific heat of the water times temperature 2 minus temperature 1 of the cold water is equal to 0.
In this experiment, we use electrical kettle, electronic balance, a big beaker, a small beaker, stopwatch, thermometer, and big container. Methodology: measure the mass of the small beaker and the large beaker by using the electronic balance. Record the mass of the small beaker and the large beaker in Table 1. Place the small beaker on the electronic balance. The water was poured into the small beaker until the water was half filled. Record the mass of the small beaker with water. Repeat step 2 by replacing the small beaker with the large beaker. Measure the initial temperature of water in the large beaker and record it in table 2. Pour the water in the small beaker into the electric kettle. Switch on the electric kettle to boil the water. After the water boils, pour back the water in the electric kettle into the small beaker. Measure the initial temperature of the boiling water in the small beaker and record it in table 2. Place the heated small beaker with water inside the large beaker. Record water temperature in small and large beakers at 1-minute intervals until temperatures are equal for 3 consecutive times.
Table 1. Data for small and large beaker. For this table, we are record the mass of the beaker and the mass of beaker with water. And then for a mass of water used, we are using the formula mass of beaker with water minus with mass of beaker. And then we got the mass of water used. Table 2. The temperature of hot water and cold water with time. This is the data that we got in this experiment. Discussion 6.1 Table and graph. This is the example calculation for the delta T hot Kelvin and delta T cold Kelvin. This is the example for the calculation of Q loss kilojoule and Q gain kilojoule. These are the data that we calculate just now. This is contain the delta T hot Kelvin, delta T cold Kelvin, Q gain kilojoule and Q loss kilojoule for each time. The next 4 slides, these are the graph that we got in this experiment. Graph 1, temperature versus time. Graph 2, rate of temperature change versus time. Graph 3, heat transfer rate versus time. And graph 4, all data versus time. This is the table 4 that we have the heat transfer rate for gain, loss, and sum for each temperature. Which is the graph 5, heat transfer rate system versus time.
Based on table 2 and graph 1, during the initial stage of the experiment, there is a significant drop in the temperature of hot water. Both lines is also intersected at around 17 minutes, indicating that the two water bodies has reached thermal equilibrium. The rate of temperature change in table 3 and graph 3 was also more pronounced when the temperature difference was larger. The temperature of hot water decreased most noticeably compared to cold water, which is due to the larger volume of cold water used in the experiment. This temperature change occurred because of the heat transfer from the hot water to the cold water as depicted in table 3 and graph 4. As we're analyzing the graph, it can be identified that the gradient of hot water, which released heat, resulted in a graph with a negative gradient. Conversely, the cold water, which absorbs heat, showed a positive gradient. So, by applying the formula Q equal mc delta T, the heat transfer for both hot and cold water is then calculated. So, for the hot water, the heat transfer was negative 2.198173 kilojoule, indicating that the heat was released. For the cold water, the heat transfer was 7.055095 kilojoule, meaning that heat was absorbed. So the heat net transfer of the entire system was 4.85692 kilojoule. In this experiment, we calculated the net heat transfer Q net between the hot and cold water. So Q net equal to Q cold plus Q hot. So 7.055095 kilojoule plus negative 2.198175 is equal to 4.85692 kilojoule. So since no work was done on the system and the volume remained constant, the work net is neglected and also assumes that there are no changes in kinetic and potential energy. So for an ideal closed system, we know that Q net is equal to delta U after we neglected the word net. Thus, the changes in internal energy or delta U of the system is equal to delta U equals 4.95692 kilojoule. Therefore, the total heat loss to the surroundings amounts also to the delta U. For the formula of percentage of energy loss to surroundings, it is equal to Q hot over Q cold times 100%. So we got 31.16%. The substantial energy loss was due to the experiment being conducted in a non-ideal environment, which is an unopened environment, because it is influenced by factors such as air movement, moisture, and fans that is also contribute to the energy loss. Second law of thermodynamics also dictates that energy spontaneously flows from regions of higher kinetic energy to those with lower kinetic energy, amplifying the observed heat dissipation.
The energy transforms from hot water to cold water to reach an equilibrium state. The energy change of a system will be zero if there is no heat loss to the surroundings. The energy change of this experiment is 4.85692 kilojoule that obtain a 31.16% of heat loss to the surrounding.
Safety procedure, protective equipment. Wear appropriate personal protective equipment, including lab coat and heat-resistant gloves when handling hot water and equipment. Second, handling hot water. Use caution when pouring and transferring hot water to avoid burns. Handle the electric kettle and hot beaker with care. Ensure that there is a clear space to move without a risk of tripping or knocking over equipment. Third, cheering precaution. Use a stir rod to ensure the even distribution of heat dissipated by the heat source. Avoid using hand or any object that may introduce contaminants. Fourth, avoiding contamination. Prevent contamination of the experiment by ensuring that the beaker are clean and free from the foreign substance before using. Use distilled water to minimize impurities in the experiment to get accurate reading. And lastly, parallax error mitigation. Minimize parallax error when reading thermometer by ensuring that the eyes are at the same level as the thermometer scale. Reference. This is the reference that we're using in this experiment.